Welcome to Beyond the Brackets. In this session, we'll be learning higher order differential equations. An equation of this form where all the pi's are constants and q of x is continuous function of x is called a linear differential equation of order n. The complete solution of this equation is given by y is equal to complementary function plus particular integral, which will also be written as y is equal to cf plus pi or y is equal to yc plus yp. This table shows the different types of roots of the auxiliary equation and the corresponding form of the complementary function for each case. Let's move on to some problems to better understand the concept. Here is the first problem. Let's call this equation as equation 1. Writing it in operator form, we replace d by dx by capital D. Then the equation becomes d square minus a square into y is equal to 0. Now, writing the auxiliary equation for this operator form, we replace d by m and equate it to 0. So the auxiliary equation becomes m square minus a square is equal to 0. This implies m square is equal to a square and hence m will be equal to plus or minus a. Therefore, the roots are plus a and minus a, which are real and distinct. If m1 and m2 are real and distinct roots, then the complementary function is given by yc is equal to c1 e power m1x plus c2 e power m2x. In this case, the roots are plus a and minus a. Therefore, the complementary function becomes yc is equal to c1 e power ax plus c2 e power minus ax. The general solution of equation 1 is given by y is equal to yc plus yp. Since the given equation is homogeneous, the particular integral yp is equal to 0. Therefore, the general solution reduces to y is equal to yc. So, y is equal to c1 e power ax plus c2 e power minus ax. Now moving on to the next problem, let us denote the given equation as equation 1. Writing it in operator form by replacing d by dx with capital D, we obtain d cube minus 3d plus 2 into y is equal to 0. To form the auxiliary equation, we replace d by m and equate it to 0. Hence, we get m cube minus 3m plus 2 equal to 0. Solving this cubic equation, we get roots m is equal to minus 2, 1, 1. So one root is real and distinct and the other is real and repeated. From the table, for a real and distinct root, m is equal to minus 2. The complementary function contributes the term yc is equal to c1 e power minus 2x. For the real and repeated root, m is equal to 1 of multiplicity 2. The complementary function is c2 plus c3x into e power x. Here, since m is equal to 1 is repeated twice, that is it has multiplicity 2, we multiply e power x by a linear polynomial in x, that is c2 plus c3x e power ax. For example, if a root is repeated 3 times, as in this case m1 is repeated thrice, it is real and repeated root, then the complementary function becomes c1 plus c2x plus c3x square into e power m1x. Again, since this is a homogeneous differential equation, particular integral becomes 0 and the solution is given by y is equal to yc. So, the complete answer is y is equal to c1 e power minus 2x plus c2 plus c3x e power x. Moving on, let us denote the given equation as equation 1. We observe that this is already in the operator form. To form the auxiliary equation, we replace d by m and equate it to 0. Thus, we obtain m cube minus 14m plus 8 is equal to 0. Solving this equation, the roots are m is equal to minus 4 and 2 plus or minus root 2. Here, minus 4 is real and distinct, so it contributes the term yc is equal to c1 e power minus 4x. The other two roots, 2 plus root 2 and 2 minus root 2 are also real and distinct. Therefore, they contribute the terms c2 e power 2 plus root 2x plus c3 e power 2 minus root 2x. Since it is a homogeneous equation, here yp will be 0. So, the solution is y is equal to yc. So, y is equal to c1 e power minus 4x plus c2 e power 2 plus root 2x plus c3 e power 2 minus root 2x. Moving on to the next problem, calling the given equation as 1, we observe that it can also be written as 4 d cube y by dx cube plus 4 d square y by dx square plus dy by dx is equal to 0. Operator form is obtained by replacing d by dx with capital D. So we get 4d cube plus 4d square plus d into y is equal to 0. To get the auxiliary equation, replace d by m and equate it to 0. 4m cube plus 4m square plus m is equal to 0. The roots of this equation are given by 0, minus 1 by 2 minus 1 by 2. Here 0 is a real and distinct root. For this, yc will be c1 e power 0x. Minus 1 by 2 is real and repeated root. So yc will be c2 plus c3x e power minus x by 2. Again, it is homogeneous equation. So particular integral will be 0. Solution will be y is equal to yc. So y is equal to c1 e power 0x can be written as 1. For the second term, we get c2 plus c3x e power minus x by 2. Moving on to the next question, call this equation as 1. We write the operator form by replacing d by dx with t to get d square plus 4d plus 5 into y equal to 0. To find the auxiliary equation, replace t with m, we get m square plus 4m plus 5 is equal to 0. Roots of this equation are m is equal to minus 2 plus or minus I, which are complex roots. Complementary function for complex roots alpha plus or minus I beta is given as e power alpha x into c1 cos beta x plus c2 sin beta x. Here alpha is minus 2 and beta is 1. So yc will be equal to e power minus 2x c1 cos x plus c2 sin x. Again, since yp is 0, solution will be y is equal to yc. So y is equal to e power 2x c1 cos x plus c2 sin x. Moving on to the last question, after naming the given equation as 1, we observe that it can be written as d square y by dx square plus 6 dy by dx plus 9y is equal to 0. To obtain the operator form, again we replace d by dx with capital D to get d square plus 6d plus 9 into y is equal to 0. Its auxiliary equation is given by replacing d with m. So it becomes m square plus 6m plus 9 is equal to 0. The roots of this equation is given by m is equal to minus 3 and minus 3. So here minus 3 is real and repeated root which is repeated twice. For this, complementary function will be yc is equal to c1 plus c2x e power minus 3x. Again, this is homogeneous equation. So yp will be 0 and the solution will be y is equal to yc, that is y is equal to c1 plus c2x e power minus 3x. This is the general solution when no boundary conditions are given. Since boundary conditions are provided in this problem, we use them to determine the values of the arbitrary constants c1 and c2. So let us denote the general solution as equation 2. The first boundary condition is y of 0 is equal to minus 4, which means y is equal to minus 4 when x is equal to 0. Substitute this value in equation 2 and simplify to get c1 is equal to minus 4. To apply the second boundary condition, we first have to differentiate y with respect to x. So y dash will be equal to c1, differentiation of e power minus 3x will be minus 3 into e power minus 3x plus c2. Here x and e power 3x both are having x, so we'll apply UV rule. First function will be written as it is, so we will write x as it is. Differentiation of e power minus 3x will be e power minus 3x into minus 3 plus second function e power minus 3x will be written as it is. Differentiation of x will be 1. Now the second boundary condition is given by y dash of 0 is equal to 14, which means x is equal to 0 when y dash is equal to 14, and we also have c1 is equal to minus 4. Substitute all these values and simplify to get c2 is equal to 2. Substituting the values of c1 and c2 into the general solution, we obtain y is equal to minus 4 plus 2x into e power minus 3x is the required solution. Practice questions with answers are provided at the end. Make sure you attempt them